Hi friends, today we are going to learn about electromagnetic induction. So let us start with the concept behind this electromagnetic induction. So assume that already we know if we have one magnet is like this, then this flux, this is assume north pole and this is the south pole. So the flux line passes and go back and coming back. Similarly here also flux line is like this. The direction will be from this and return back to here, and similarly we can have this is and return back to here. So this is the magnetic flux line. It will passes out from here, and this is the magnetic flux coming in. So this is the arrow mark like this. That's why the magnetic flux line passing out is called it as north pole, and just opposite coming in this called as south pole magnetic flux. So now assume that we have now electromagnetism also one of the important concept. So here if you see this, see now we have the winding. Let us say now, let me take in another one color. So if you take this another one winding, this is the winding. Okay, so in this winding I have connected here one galvanometer. Now this magnet, already we know this flux line how it will pass. So now we are taking this magnetic magnetic bar. This is a bar magnet, right? So this is the north pole and this will be the south pole. So now I am moving very fast inside this winding. When I move this magnetic path, already the flux line will pass as like I have explained here. So when I move very fast inside this winding, very fast, there is the galvanometer will start to deflect. Maybe for example this is the galvanometer, and first this is the null position, this is positive 5 or negative 5, like that if you make it. So this initially it is in the null position. Once we move this inside this this winding very fast, this position, this needle position will, new position will be like this. Then when I keep inside as such, for example if we are taking this magnet, now we are forcing inside very fast, that time there is a deflection. Now the same magnet I am keeping it inside, so the north pole here and south pole here. So the flux line will pass on this. So at the same time, as we are keeping in the same place without any movement, we can see again the next deflection of the galvanometer will be in this position only, in the zero position only. Similarly, when I take this magnet outside very fast, what happen? Again this deflection will turn to right side. That means the new deflection will be turned to right side. So from this, Faradays have seen some Faraday's law of electromagnetic induction has come into the picture. That means whenever the magnet is moving, whenever this magnet is moving inside this winding, there is a change in flux. The rate of change of flux will happen. So this due to the rate of change of flux, that induced EMF, there is a current flow in this winding, so that the galvanometer is showing deflection. So if we move this magnet very fast, the rate of change of flux with respect to time is very fast, therefore the deflection will be more. At the same time, if we make this magnet in this particular position without any movement, we can say that rate of change of flux with respect to time is equal to 0. Similarly, when we take it out, again the rate of change of flux with respect to time will increase. Therefore, again there is having some rate of change of flux. So from this, what is meant by electromagnetic induction is the induced EMF in this electromagnet is directly proportional to the rate of change of flux with respect to time. That is, induced EMF is directly proportional to the rate of change of flux with respect to time. Whenever the bar magnet is stationary, that time there is no flux. Even though this is inside the rate, there is no change in flux. Not like no flux, there is no change in flux. Therefore, the rate of change of flux with respect to time is equal to 0. Therefore, induced EMF is 0. Whenever we are moving this magnet inside this bar, inside this winding, there is a rate of change of flux. It will create an induced EMF in the winding. That's why galvanometer is showing the deflection. So from this, we can conclude that the rate of change, we can conclude that this induced EMF is equal to directly proportional to d phi by dt. Then induced EMF, the constant of proportionality is called as n into d phi by dt. So n is nothing but number of turns in the winding. So when the number of turns is more, induced EMF is more. When the number of turns is less, induced EMF will be less. Then this is not the final answer for the induced EMF. So we have to learn Lenz law. The Lenz law also give a good impact on the induced EMF. So what the Lenz has done, the scientist Lenz, what he has done, here this is the magnet. Already we have the winding. So already told you that when the magnet is near to this winding, okay, when the magnet is near to this winding, what will happen? This magnet, already we know, as this winding is going, this magnet is there. Due to this permanent magnet, there is a flux linkage, right? There is a flux linkage. Due to this, there is having one induced EMF. That induced EMF is nothing but E is directly proportional to N into d phi by dt. Due to the induced EMF, there is a current flow. For example, assume that the current flow is now this direction. Assume that current flowing in and current flowing out. So there is a current flow. Here we have connected the galvanometer. So the current flow is in this direction. So what happened during this time? We have with this, when this magnet is moving near to this, already I told you, when the magnet is stationary, there is no induced EMF. So when we are moving near to this, current flow is in this direction. At the same time, when I am moving from this magnet, when I am moving away from the winding, for example, this is the winding and I am moving away from the winding. This is the north pole and south pole. Here the distance is very less. Here the distance is more. When I move this magnet away from the winding, the current direction was reverse. That means current is moving like this and current is coming out like this. So what he found out, that when the magnet is near to that, it will create one opposing force, the induced EMF, which will create the opposing force. That means here, whenever this is north pole, this coil here, this is north pole and south pole. So due to that, the current direction is like this. Already we know when the flux is like this, current thumb rule, when the flux is like the direction of the four fingers, then the thumb finger direction is the direction of the flux. Similarly, so this will oppose the flow of flux. That means we will call this is the main flux. So I can say when this the flux created by the magnet is the main flux, right? So this flux, so the induced flux is opposing the main flux. Similarly, when we are moving this magnet away from this, it will automatically south pole and north pole. That means the current direction is reversed. That is why when this experimentation, if you see this, whenever the galvanometer is magnet is moving towards the winding, galvanometer reflection is towards the anti-clockwise direction. Whenever the magnet is moving away, this reflection is clockwise direction. Galvanometer reflection is clockwise direction. So from this we have to conclude that induced EMF in the winding is creating the flux. That flux opposes the main flux. That is why that induced EMF is equal to minus n into d phi by dt. Induced EMF is equal to minus n into d phi by dt. So this is one of the important definition of the Faraday's law of electromagnetic induction. So the Faraday's law of electromagnetic induction having two concepts, that magnetic induction as well as Lenz law. So first one is whenever the magnet is moving, then only the rate of change of flux will happen. Therefore induced EMF is directly proportional to rate of change of flux. When the magnet is in stationary, the induced EMF, the rate of change of flux is equal to 0. Therefore induced EMF 0. Similarly, when the magnet is moving near to this winding, that created induced EMF create one flux. That flux will oppose the main flux. Therefore we will write it as this current direction will be the clockwise direction, or otherwise galvanometer deflection is in the anti-clockwise direction. At the same time, when the magnet we are moving, so that the poles, the direction will be changed in the electromagnet, so that what happen, it will south pole this side and north pole in the left side. Therefore the galvanometer shows in the positive direction, or otherwise clockwise direction. So I hope this concept is very much understandable. So in this description I will show you the two animation video link. You can go through it and understand what is meant by electromagnetic induction and this Lenz application of Lenz law. I hope the topic is understandable, and if you like this channel, kindly share it and subscribe it. Wish you all the best. Thank you.